Okay, this is section 5.5, and this is the first part of section 5.5, and we're mainly going to talk about the double angle identities. We've already talked about the sum and difference identities, and we use those when we're trying to find the exact value of an angle that's not found on our unit circle. For example, 75 degrees. And we learned that we could find, say, the sine of 75 degrees by adding our 45-degree angle plus 30 degrees. Okay, and we would use our sum identity to find the exact value. And so now we're going to start talking about our double angle formulas. So the first thing I want to do is I want to show you where these formulas came from. So you need to copy this down on your notes as I do this. So let's do sine 2u first. So let's do our double angle identity for sine. And if I wanted to rewrite this, does it make sense? I could rewrite this as sine u plus u, because u plus u is 2u. Well, this is a sum identity. Okay, so looking at your sum identities from section 5.4, I'm going to substitute, instead of u and v in, it's u and u. So my sum identity for sine is sine u times cosine u, which is my second angle, plus cosine u times sine u. All right, now I'm just going to simplify this. Do you see that this is the same thing, sine u cosine u plus sine u times cosine u? So that gives me two of those, 2 sine u cosine u. And you see that up in our identities, that's what it's equal to. Sine 2u is 2 sine u cosine u. Okay, so let's do cosine 2u. Now if you notice, in our formulas, we have three different ones. Okay, so I'm going to show you how they come up with those. Same thing, I can rewrite my 2u as cosine u plus u. And again, I'm going to use my sum identity for cosine. My sum identity for cosine says cosine u times cosine u minus sine u times sine u. And when I simplify this, cosine times cosine we know is cosine squared u, minus sine times sine is sine squared u. And if you'll notice, that's what our first one has. Okay, so now let's see where they got this one. Let's do the other one for cosine 2u. Ooh, I don't like that color. Let me get a different color. All right, so cosine 2u. All right, so we already found out that it's cosine squared u minus sine squared u. So let's substitute what we know is equivalent to cosine squared u. Well, cosine squared u, isn't that the same thing as 1 minus squared u? 1 minus sine squared u? So I'm going to substitute 1 minus sine squared u for my cosine. And then I have my minus sine squared u. Okay, now I can combine like terms. All right, I have 1 minus sine squared u and another sine squared u is 2 sine squared u. And there's that identity, 1 minus 2 sine squared u. Okay, let's do our next cosine 2u. So cosine 2u, if I take this, we know that it was cosine squared minus sine squared. All right, so I'm going to keep this cosine squared u minus, and I'm going to replace this with the Pythagorean identity. We know that sine squared u is the same thing as, what, 1 minus cosine squared u? So when I simplify, I get cosine squared u, distribute your negative, and I have negative 1 plus cosine squared u. And so when I add my cosine squareds together, I get 2 cosine squared u minus 1. And if you'll go back up and look at your identities, there it is. Okay? And we'll go ahead and do tangent u. I'm going to do it right over here. So again, I'm going to write tangent to u as tangent u plus u. And using my sum identity for tangent, I know that it is tangent u plus tangent u all over 1 minus tangent u times tangent u. So tangent u plus tangent u on top, that gives me 2 tangent u's. And then 1 minus tangent times tangent is tangent squared. And that gives me the identity that they told me. Okay? So all of those double angle identities come from our sum identities that we did in section 5.4. All right, so now I'm going to show you how we can use these to help us solve equations. Example 1 says solve 2 cosine x plus sine 2x equals 0. Okay, so the first thing I see is I have a double angle here, sine 2x. Okay, so I want to rewrite sine 2x with what it's equal to in my double angle identities. So I'm going to rewrite this. 2 cosine x plus, and then your double angle identity, sine 2x is 2 sine x times cosine x. So I replaced this for my sine 2x. And I'm going to set that equal to 0. Now we're back to solving just like we have been. I'm going to look and see, does this have something in common that I can factor out? Well, I can factor out a 2, and they each have a cosine x. So I have 1 plus 2 sine x equals 0. Okay, now I'm going to set each factor equal to 0. 2 cosine x equals 0. 1 plus 2 sine x equals 0. I'm going to solve for sine and cosine for both of them. So cosine x equals 0 divided by 2 is 0. Subtract 1 and I get 2 sine x equals negative 1. Divide by 2 and I get sine x equals negative 1/2. Now remember what we're looking for. This is not our answer. We want to know at what angle is cosine equal to 0 and at what angle is sine equal to negative 1/2. Okay, so let's do cosine equal to 0 first. Okay, we should know that in our unit circle, cosine is our x value, and our x value is 0 at pi over 2 and 3 pi over 2. So for this problem, x is equal to pi over 2, and x is equal to 3 pi over 2. Now, since it did not give us an interval, I'm going to write the general solution. So we know that the period for cosine is 2 pi. So that's going to be pi over 2 plus every 2 pi after that. And then it's going to be 3 pi over 2 plus every 2 pi after that. So there's 2 of my answers. And then I need to figure out where is, I want to make sure I didn't make a mistake on this. Hang on one second. I want to make sure I didn't write something down wrong. Okay, I did make a mistake. I knew this wasn't going to turn out right. When I factored out this 2 right here, Okay, this 2 is now gone. So this 2 right here is no longer there. So sorry, I'm going to fix that. That little 2 right there is gone. This little 2 right there is gone. So do you see I just have sine x equals -1? Okay, because I factored out this 2 and that should be gone. Okay, so I want to know where is sine x equal to -1? Okay, well, sine is my y value, and my y value is -1 at 3 pi over 2. And you see that 3 pi over 2 is already listed, and the period for sine x is also 2 pi, so this also covers my answer for this problem. So that's my answer for example 1. Example 2. Example 2, I believe on your sheet, it tells you just to go from the interval from 0 to 2 pi. So I'm looking to solve for x, and I see a double angle sine 2x. I can replace sine 2x with a double angle identity. All right, so sine 2x can be replaced with 2 sine x cosine x. Then I have this minus sine x equals 0. So I'm going to look and see what do they have in common. What can I factor out? Well, I can factor out a sine x. Now I'm going to write down what I have left. In this term, I have a 2 cosine x. This term, everything's factored out, so I have a 1. Now I'm going to set each factor equal to 0. Okay, so this one's already solved, so I need to figure out between the interval of 0 and 2 pi, not including 2 pi, where is sine x equal to 0? We know that sine x, sine is my y value, so my y value is 0 at 0 and at pi, and again at 2 pi, but I'm not including 2 pi. So for this answer, x equals 0, x equals pi. Now I'm going to solve this one. So I'm going to add 1 to cosine x equals 1. Cosine x equals 1/2. So now I have to figure out where is cosine positive 1/2. Well, I know cosine is positive in the first quadrant and the last quadrant. We also know that cosine is adjacent over hypotenuse, or x over my hypotenuse. And when I use Pythagorean theorem, I don't even have to use Pythagorean theorem. If I know this is 1, when I use Pythagorean theorem, that's 4 minus 1, that's square root of 3. Okay, so opposite my 1 is always 30, so this right here must be 60 degrees. So my first answer I want is 60 degrees, but we're not going to list it as 60. That is pi over 3. And then we want this angle all the way around, or 300, which is 5 pi over 3. Okay, example 3. Use the following to find sine 2 theta, cosine 2 theta, and tangent 2 theta. All right, so first of all, they told us cosine theta is 5 over 13, and then they told us which quadrant we're in. 3 pi over 2 to 2 pi, we're in this fourth quadrant over here. So cosine is adjacent over hypotenuse. So when I use Pythagorean theorem, that means this side right here has to be -12, and it's negative because I'm in this fourth quadrant. All right, so sine 2 theta, I'm just going to rewrite the formula for that. Sine 2 theta is 2 times the sine of theta times the cosine of theta. Well, I know what cosine theta is, but they didn't tell me what sine theta was. But I can figure it out from looking at my drawing. Sine theta is opposite over hypotenuse, so it's -12 over 13. So I'm going to plug those numbers in. 2 times sine theta, which is negative 12 over 13, times cosine theta, which is 5 over 13. And now that just becomes a multiplication problem. When I multiply straight across, what is that? Negative 120 over 169. Okay, and those were reduced, but I'm not going to be picky about reducing your fractions. So that's sine 2 theta. Now let's find cosine 2 theta. Cosine 2 theta, I have 3 different formulas I can choose from. Okay, it doesn't matter which one you want to do. I'm going to do this one. Cosine squared theta minus sine squared theta. So cosine is 5 over 13 quantity squared minus sine theta is negative 12 over 13 quantity squared. So this is 25 over 169 minus 144 over 169. So 25 minus 144, negative 119 over 169. Okay, now we're going to do tangent to theta. Now, tangent to theta, I can use the formula for tangent to theta, or since we know sine 2 theta and cosine 2 theta, couldn't I just say that it's sine 2 theta divided by cosine 2 theta? So sine 2 theta was negative 120 over 169 divided by cosine 2 theta, which is negative 119 over 169. So negative 120 over 169 times the reciprocal. So my answer is 120 over 119. Okay. Last example, example 5 or 4. Okay. Basically the same exact thing. They first tell us find the sine of theta. Sine is opposite over hypotenuse, 3/5. Cosine is adjacent over hypotenuse. So now they want us to find cosine 2 theta. Okay, well I'm going to use this formula for cosine 2 theta. Cosine squared theta minus sine squared theta. Cosine is 4/5. Sine is 3/5. So I have 16 over 25 minus 9 over 25. So what is that? 7 over 25? Okay, so let's do one more. Let's do sine 2 theta, and I'm going to have you guys do the rest. Sine 2 theta I know is 2 times sine theta times cosine theta. So I have 2 times sine theta, but sine is 3/5. Cosine theta is 4/5. So that's going to be 6 times 4, 24 over 25. Now to find secant 2 theta, can't you just flip over your cosine? It's the reciprocal of cosine. Cosecant is the reciprocal of sine, so that would be 5 over 3. Secant is the reciprocal of cosine, so that's 5 over 4. Cotangent, we didn't find tangent, so you need to find tangent first by saying sine over cosine, or sine 2 theta over cosine 2 theta, and then use the reciprocal. I'm going to have you finish part G. Okay, that's it for the first part of section 5.5, double angle identities.